Hi everyone, in this video we're going to be looking at our tutorial 6 suggested solutions. Okay, so before we get started with the actual tutorial questions, I would like to just briefly go through this concept of mutex, okay, to make sure that we understand. Okay, so what I have here is we have created a mutex object here, okay, and both the threads LED red thread and LED green thread are accessing a shared resource, which is the RGB LED, okay. And what we are saying is, in order to make sure that each thread has exclusive access to the shared resource, before we access this shared resource, we call OS mutex acquire, okay, and we wait forever, and subsequently once I finish I release, okay, and that's the same thing I do over here, okay. And this works, okay, because the moment one thread acquires the mutex, okay, when I get context switch out to the other thread, okay, it will not be able to acquire the mutex, so it cannot access the shared resource, okay. So that is the basic idea of having a mutex, okay, to protect access to a shared resource. Okay, but what if, okay, the scenario that I'm going to give you is, what if the LED red thread follows the protocol of access, which is I lock, okay, access, and then I release, but the LED green thread does not follow this protocol. In fact, it totally does not even bother with calling OS mutex acquire and calling OS mutex release, okay. So let's assume that LED green thread, okay, is written this way. What would happen? Okay, so basically what would happen is, after the red thread acquires the mutex and I switch on the red LED, as we know with RTX RTOS, we have a context switch, okay, because they are the same priority. When I switch over to the LED green thread and I start executing, the LED green thread does not attempt to deal with the mutex. It straight away goes in and tries to control the shared resource over here, and it will get access to the shared resource because there is no protection mechanism that it is following, okay. So the protection mechanism is actually the mutex, but since it is not using the mutex, it will still get access to the shared resource, okay. So this is an important concept, okay. When we created this mutex, okay, we had that idea that this was tied to the RGB LED, okay. This link between the mutex and the RGB LED is only in the programmer's mind, okay. Only the programmer or the software developer knows that I created this mutex and this mutex is tied to this RGB LED, okay. So in that context, whenever I'm trying to access this RGB LED, I should make sure I lock the mutex and unlock the mutex, okay, before and after, okay. So this is important, because the software or the OS does not have any idea why you created the mutex or for what shared resource you're going to use it for, okay. Only the programmer knows. So it's the programmer's responsibility to ensure that if I create a mutex with the intention of protecting a shared resource, then I must make sure that every thread that tries to access this shared resource goes through the process of locking and unlocking it, okay. So that is the proper usage of mutex. Okay, so I just wanted that concept to be clear, okay, to all of you. Okay, in our first question for this tutorial, we basically have three threads being created. One is a high priority thread, one is a medium priority thread, and this is a low priority thread, okay. And we are going to analyze and see what is the behavior, okay, of this task over time, okay. So I think the next slide with the picture shows a lot clearer, okay. So let's look at the timeline, okay, and relate back to the code, okay, to have a better idea of what is really happening here, okay. uh, when uh, when all three tasks are running in the system, so assuming from time t equals 0 all three tasks are in the system already, okay. Since high priority thread here is the highest priority, that will get a chance to run, okay. So that is what you see over here, okay. And the medium priority and the low priority are both there in the system, but they are not able to run yet, so they are in the ready state, okay. So that is over here and over here, okay. So that is what is happening in the first time slice. And once the high priority thread runs, once it starts to run, it calls the OS delay, okay, for 1000 seconds. So this is the point where I call OS delay. And once I call OS delay, I am blocked. Okay, I'm blocked for 1 second. Okay, I'm blocked for 1 second. And at that point of time, what will happen? You will invoke the scheduler to do a context switch. Okay, so when the context switch happens, I will be able to execute the medium priority thread. Okay, so that is why from here I do a context switch and I allow the medium priority thread to run. So the medium priority thread will run, and the first thing it does, it also calls another OS delay of 1 second. So over here I'll call OS delay of 1 second, and I'll block myself for 1 second. So since both the high priority and medium priority threads are blocked, the low priority thread will now get a chance to run. Okay, so that is what's happening. So when I go to a block, I will do a context switch and the low priority thread will get a chance to run. When the low priority thread is running, what does it do? It acquires a mutex, okay, which is this point here. And after it acquires the mutex, it calls OS delay for 5 seconds. Okay, so it's going to delay itself for 5 seconds. So there will be a period of time, as you can see over here, there will be a period of time where all the tasks are in a block state and no task is actually running. Okay, and what will happen is the high priority thread, which call the OS delay first, would come out of the OS delay, correct? Because both are 1 second, high priority and medium priority are both 1 second, but the high priority thread called it first, so it will come out of the 1 second first. So once it comes out, it will go to ready state, and from ready state it will go to the run state. Okay, so once it goes to a run state, it goes and tries to call this OS mutex acquire. And what will happen is the mutex was already acquired over here by the low priority thread. Okay, so since it cannot fulfill this request and we said wait forever, okay, we will become blocked. Okay, so from this point onwards, it will become blocked. Okay, and since the high priority thread becomes blocked, okay, it will give up the CPU, and around that time, okay, we also know that the medium priority thread will be coming out of the OS delay. So while the high priority thread was running, the medium priority thread would have also finished its OS delay of 1 second and come to the ready state. And once the high priority thread becomes blocked, okay, so at this point of time, when it tries to do the acquire and becomes blocked, I will be able to do a context switch to the medium priority thread, and medium priority thread will be able to run. Okay, so you have to understand that the context switch in this situation occurs because the high priority thread ran and attempted to acquire a mutex but was not able to do it, and so the context switch happened. And since medium priority thread also had come out of the block state and was in the ready state, we switched over to the medium priority thread. Okay, and now we are running. And in the medium priority thread, we are doing non-blocking stuff. That means basically things not related to the mutex in this situation. And so what is happening is it will continue to use the CPU. And we know the low priority thread was blocked for 5 seconds. And after 5 seconds, eventually it will come out of the block state. And when it comes out of the block state, it will go to a ready state. Okay, but since the medium priority thread is continuously running, okay, and is not giving up the CPU for any reason, there is no opportunity for the low priority thread and to come and execute this. Okay, so this OS mutex release would never get a chance to run until the medium priority thread gives up the CPU. Okay, but that is not shown here. Okay, so because the medium priority thread is continuously running, okay, doing non-blocking stuff. Okay, so that is basically the scenario that will be observed if you try to execute this code. And this is basically what we call priority inversion. Okay, why is it priority inversion? Because a high priority thread is actually blocked because of a low priority thread. Okay, and why was it blocked? Because the low priority thread acquired a mutex that was shared. So this mutex is shared by, or this shared resource across both the low priority and high priority thread caused the low priority thread to acquire the mutex first in this situation, and because of that happening, when the high priority thread was able to run, it was not able to acquire the mutex, and then it got blocked. Okay, so the whole cause for this is both the low priority and high priority tasks are having a shared resource, and to gain access to this shared resource, both of them must acquire the mutex and then release the mutex. Okay, and the sequence of the code execution that we saw allowed the low priority thread a chance to run and acquire the mutex first. Okay, so eventually when the high priority thread was able to run, it was not able to acquire the mutex, and thus it became blocked. Okay, so that is what we call a priority inversion problem. Okay, and it's quite a serious problem because uh, it sort of goes against the whole idea of assigning priorities to our task, because when we assign priorities to our task and we say this is a high priority task, we expect it to have very immediate access to the CPU whenever it needs. Okay, but in this case, a high priority task is blocked by a low priority task, so it can sort of really jeopardize the whole dynamics of the system and how you planned for it to execute. So in RTX RTOS, we can enable this thing called priority inheritance. Okay, and what is this priority inheritance? It allows a low priority thread to be raised to the same level of a high priority thread the moment the high priority thread becomes blocked due to the shared resource already being acquired by a low priority thread. Okay, so let me explain that in the picture earlier. So what we are saying is, if I were to enable priority inheritance, okay, so priority inheritance, okay, so if I were to enable this priority inheritance, then what would happen is, at this point of time here, the high priority thread is blocked, okay, because of a shared mutex, okay, a shared resource between the high priority and low priority thread. So at this point of time, what would happen is the OS will come in, and at this point it will raise the priority of the low priority thread to be the same level as that of the high priority thread. Okay, and why that is important is because when the low priority thread eventually comes out of the block state, it will be able to preempt the medium priority thread and get a chance to run. Okay, when it gets a chance to run, it can give up the mutex. Okay, and once it gives up the mutex, okay, it will automatically come back down to this same priority level. Okay, and once the mutex is given up, it will then be able to be acquired by the high priority task, and the high priority task can then carry on. So what you will see is the medium priority thread will no longer have a chance to run indefinitely, okay, hogging the CPU and preventing the low priority task from running. Okay, so that is basically the whole idea of this priority inheritance mechanism that is already built in the RTX RTOS. Okay, so that is the good part. It's already built in. You do not need to explicitly worry about implementing any additional code, okay, to implement this feature. It's already built in into the RTX framework. Okay, in our next question, we're going to be looking at semaphores. Okay, so semaphores, what are semaphores? Semaphores are basically a mechanism, okay, to control access to a group of shared resources. Okay, and the easiest analogy I can think of is, okay, for example, you have 3 car park lots. Okay, so these are car park lots. Okay, and I have 5 cars. Okay, so assuming I got 5 cars and I got 3 car park spaces. So who gets to park? Okay, if I fix if I have a fixed allocation scheme, what happens? That means I can only pre-select maybe 3 cars and say only these 3 cars can park here, the other 2 cars cannot park here. Correct? So that is one approach, but then that will not be a way to manage it if I really wanted all 5 to have a chance. Correct? So what I can say is, I can say we have a system where whoever comes first and asks for a car park slot can take it, correct? So if this car comes first, then I will take one slot. If this car comes second, then I'll take another slot, and then this car comes, I'll take another slot. When all the slots are full, then the other cars must wait until somebody leaves, then I can take the available slot. So that is the whole idea of semaphores. Okay, you are controlling access to a group of resources that are shared. Okay, so that is the general use of semaphores, which is also explained in the lecture slides. Okay, in this tutorial in the lab, we are also going to be looking at another aspect of using semaphores, which is synchronizing. Okay, that means how can I make one task? So as we know, if I have task 1 and task 2 running, okay, context switches and things can happen very dynamically in an OS system, correct? But what if I want task 1 to run and then maybe wait, okay, wait until task 2 has finished some level of completion, then I want to be able to carry on. Okay, so how can I synchronize one task with another task? Okay, so that is what we're going to be looking at. Okay, so let's look at the code given uh, uh, in the lab as well as the tutorial. So what you have here is in the main, you have created a semaphore. Okay, so this is the max count and this is the initial count. So in this example, the initial count is 0 and the max count is 1. Okay, and I've integrated the code from the earlier lab where we have the push button IRQ handler. So if you look at both the threads, okay, the first thing that both the threads do is they attempt to acquire the semaphore. Okay, so in this situation, the initial value of semaphore is 0. Okay, so when I try to acquire a semaphore when the initial value is 0, what will happen is you will not be able to get the semaphore, so it will become blocked. Okay, so the thread here will become blocked. Similarly, when the LED green thread comes, it tries to acquire a semaphore and then it also becomes blocked. Okay, now the port D IRQ handler, basically what it does is whenever the push button is pressed, then I release a semaphore. So when the semaphore is released, it goes to the task that was in the queue waiting for the semaphore. Currently both of them are in the queue, but the LED red thread came first, so the LED red thread will get the semaphore and it will come out of the block state and be able to execute. Okay, and subsequently when it loops back, it will join the queue again. Okay, and the next time I press a button, what happens? Since LED thread was already serviced, the LED green thread's request for the semaphore has moved up to the front of the queue. So it will now get the semaphore and it will complete its code and then be able to loop back and wait for the semaphore again in the next iteration of the loop. Okay, so that is basically what is happening here. Okay, and in terms of timing diagram, this is what we have. Okay, so this is basically what I explained just now, where the red LED thread is the first one to ask for the semaphore, okay, and then followed by the green LED thread. Okay, and since they are both in the queue, they are both waiting for the semaphore. When the button is pressed and the semaphore is released, the first person in the queue, which is the red LED thread, is the one that comes out of the block state and is able to run. Okay, subsequently when I have another push button press, again I will release the semaphore and the green LED thread will run. Okay, so that is basically the timing sequence or timeline of execution, okay, for the code that is given. Okay, so if you press the button once, it will light up with the red LED, and after that the next button press will light up the green LED and the whole sequence will keep on repeating. So this is basically the observation that you will make, okay, you will see in the lab. So what happens if the button is pressed again when the red LED is lighted up? So what we are saying is, what if I move this entire chunk and the push button, if I moved it up to around the same time when the red LED was switched on. Okay, so while the red LED is on, I press the button again. then what happens? Then the semaphore would have been released and this thread would have run, and since they are both of the same priority, they would have run concurrently, and so you would have seen that it would be red for a while followed by both red and green, so you would have seen yellow for a while, and subsequently the red will go off and then you will only see green. Okay, so that is the observation that you can observe if I try to press the button again while the red LED was still lighted up. Okay, so that explanation is what is given here. Now, for question 4 and question 5, basically we are now trying to change the behavior a bit. Okay, so the first question 4, what we want is we want the behavior such that whenever the button is pressed, the RGB LED lights up as yellow for 1 second and then goes off. Okay, so that is the first objective. For question 5, what we want is whenever the button is pressed, the red LED lights up first, and then after it goes off, the green LED must light up. Okay, so there is no overlap in this situation, but one button must trigger the red, and after the red finish, then they trigger the green. Okay, so that is the objective. For question 4 is every time a button is pressed, both of them will light up together, so I will see yellow. Okay, so how do I achieve this outcome? Using only semaphores. For question 4, what I can do is I can increase the semaphore count, max count to 2. Okay, and every time a button is pressed, I release I call over semaphore release 2 times. So what will happen is it will increase the count by 2, which means 2 tasks that are in the queue will be able to get a semaphore. Okay, so both the red LED thread and the green LED thread both will be able to get a semaphore and come out of the block state. Okay, and then eventually run concurrently. Okay, so that is how I can achieve the objective for one button press and making 2 threads get unblocked at the same time. Okay, for question 5, what I wanted was a sequence, red first, and after red finishes and goes off, then the green must light up. Okay, and what I can do is in this situation I change back my max count to 1. Okay, and whenever a button is pressed, the red LED thread will get the semaphore, and once the red LED has been on for 1 second, and I will release the semaphore and then off the LED. So what will happen when I release this semaphore, it will trigger the green LED thread to be unblocked. Okay, so about the time when the red LED goes off, the green LED will become ready. Okay, and it will be able to light up. Okay, so what you will see is the red LED will light up for 1 second, and at that time, when the time expires, the another semaphore is released from the LED red thread, which will then unblock the LED green thread. Okay, and allow the green thread to run, okay, for its duration and light up the green LED. Okay, so you will see the sequence: red LED on, then green LED on. Okay, so that is basically the sequence that you will observe with this scenario here. Okay, so basically if you look at how we are using semaphores, we are using them in the context of performing some form of synchronization between tasks. Okay, so this is what I explained just now. Even though semaphores are generally used for managing resources, you can also use them in this context of managing the sequence of events. Okay, because in a multi-threaded environment, things are very dynamic. Okay, so you may want some task to wait for some activity to be completed before it carries on. So using semaphores, you can sort of achieve this outcome. But again, this is not the only option. Okay, so in subsequent tutorials, okay, you're also going to be learning about threads and events and message queues and so on. So those are also very useful mechanisms to achieve these kind of objectives of synchronization and data passing, data communication between threads. Okay, so that brings us to the end of this tutorial. So thank you very much. I'll see you in the next class.